October 10th, 1943. 20,000 feet above Bremen, Germany. The temperature outside is minus 25 degrees Celsius, cold enough that exposed skin freezes in seconds, cold enough that machine gun lubricants congeal into useless sludge, cold enough that blood from wounds freezes before it can drip. Inside the B-17 Flying Fortress, Memphis Belle de Sanu, Staff Sergeant Joe Sarnowski, the flight engineer and top turret gunner, is staring at a problem that should mean the aircraft is going down. The number 3 engine, the inboard engine on the right wing, has been hit by 20mm cannon fire from a Focke-Wulf 190 that came screaming through the formation 5 minutes ago. The cowling is shredded, oil is streaming back across the wing, and the propeller is windmilling uselessly, the engine dead. But that's not the problem that has Sarnowski's full attention. He's seen engines shot out before. You feather the prop, shut down the fuel, and fly home on 3 engines. A B-17 can make it back to England on 3 engines, even on 2 if the pilot is good and you're not too shot up. The problem is what the 20mm round did after it killed the engine. The explosive shell penetrated the engine, detonated, and sent shrapnel tearing through the wing structure behind the engine. Sarnowski can see daylight through holes in the wing where there should be solid metal. More critically, he can see fuel streaming from multiple punctures in the wing fuel tank, creating a vapor trail that extends 30 feet behind the aircraft. They are hemorrhaging aviation gasoline at approximately 20 gallons per minute from wounds that conventional repair cannot fix at 20,000 feet. Every manual, every training evolution, every instructor at technical school says the same thing. Catastrophic fuel tank damage means you bail out. You cannot repair pressurized fuel tanks in flight. The fuel system is sealed and pressurized to prevent vapor lock at high altitude. Once that seal is breached by battle damage, the escaping fuel creates vapor that is explosive. The pressure loss prevents proper fuel flow to the remaining engines, and the fuel loss means you will not have enough to reach England, even if the engines keep running. The navigator has done the calculations. At current fuel consumption, including the losses from the damaged tank, they have approximately 40 minutes of flight time remaining. They are 90 minutes from the English coast. The mathematics are simple and brutal. They will run out of fuel over the North Sea, 50 miles from safety, and ditch in water where survival time is measured in minutes before hypothermia kills everyone who survived the ditching. The pilot, Lieutenant James "Mac" Macaulay, has already given the order to prepare to bail out over Germany. Better to become prisoners of war than die in the North Sea. The bombardier is preparing to jettison the bomb site so it won't fall into German hands. The radio operator is destroying codes and burning classified materials. The crew is preparing to abandon ship, but Sarnowski is staring at the streaming fuel, at the holes in the wing, at the shredded metal, and he's thinking about something that has nothing to do with Army Air Force's technical manuals or approved repair procedures. He's thinking about his father's garage in Pittsburgh, where he worked as a mechanic before the war. He's thinking about a technique his father taught him for temporarily patching a leaking radiator hose using friction tape and rapid-setting gasket compound. He's thinking about whether the same principle might work on a fuel tank at 20,000 feet, with 200 bullet holes in the aircraft and fuel vapor creating an explosion hazard. In his flight suit pocket, Sarnowski has something that no regulation says a flight engineer should carry, but that every mechanic who's worth anything carries anyway: a roll of duct tape. Military specification duct tape, designed for everything from sealing heating ducts on aircraft to emergency repairs on equipment. Strong, adhesive-backed cloth tape that sticks to almost anything and creates an airtight seal. And in his toolkit, secured next to his gun position, he has a tube of high-temperature gasket sealant that's supposed to be for minor engine maintenance between missions. He has an idea. It's insane. It violates every safety protocol about working with leaking fuel. It requires climbing out on the wing through the access panel, working in minus 25-degree cold at 20,000 feet without a safety line, and trying to patch holes while fuel is actively spraying and creating explosive vapor. If he creates a spark, if the vapor ignites, if he makes any mistake, the wing will explode and kill everyone on the aircraft instantly. But if he doesn't try, they're bailing out over Germany, becoming POWs for the rest of the war, losing the aircraft, and possibly losing crew members who are too badly wounded to safely parachute. Sarnowski keys his throat mic. "Pilot, this is engineer. I think I can patch the fuel tank. Give me 10 minutes. The pilot's response is immediate. "Negative. That's suicide. We're bailing out." Sarnowski's counter. Sir, we bail out. We're POWs for however long this war lasts. We ditch in the North Sea. We're dead from hypothermia in 20 minutes. The fuel leak is creating vapor, but it hasn't ignited yet. If I can patch enough holes to slow the leak, we might make it home. Let me try. If it doesn't work, we bail out then. But let me try. A long silence on the intercom. Then, you've got 10 minutes. After that, we're bailing out whether you're done or not. Be careful out there, Sarnowski. Over the next 12 minutes, as German fighters continue to harass the formation and flak bursts around them, Staff Sergeant Joe Sarnowski will climb out onto the wing of a B-17 at 20,000 feet, working in temperatures cold enough to kill him in minutes, using duct tape and gasket sealant to patch fuel tank holes that conventional wisdom says cannot be patched in flight. He will create a repair technique that Army Air Forces engineers will initially refuse to believe worked, that will be classified and studied after the war, and that will save the lives of his entire crew and bring a $1 million bomber back to England when every procedure said it should have been abandoned. How does one mechanic with duct tape and sealant repair catastrophic fuel tank damage in flight conditions that should make the work impossible? What was the tape trick that defied engineering principles and saved an aircraft that should have been lost? And why did this repair, executed in 12 desperate minutes at 20,000 feet, become a legendary example of American improvisation that changed how the Army Air Forces thought about battle damage and in-flight repair? This is the story of the man who fixed the unfixable, the duct tape technique that saved 10 lives and a flying fortress, and the 12 minutes that proved sometimes the craziest idea is the only idea that works when the book says you're already dead. While Joe Sarnowski was growing up in Pittsburgh during the 1920s and 1930s, working in his father's garage and learning that every mechanical problem has a solution if you're creative enough and willing to try unconventional approaches, the world was developing the strategic bombing doctrine that would eventually bring him to 20,000 feet over Germany in a damaged bomber. After World War I, military theorists like Italy's Giulio Douhet and America's Billy Mitchell argued that strategic bombing, attacking an enemy's industrial capacity and civilian morale directly from the air, could win wars without the need for massive ground campaigns. By the 1930s, the United States Army Air Corps was developing heavy bombers capable of carrying large bomb loads over long distances at high altitude, theoretically beyond the reach of enemy fighters and most anti-aircraft fire. The Boeing B-17 Flying Fortress, first flown in 1935 and refined through multiple versions, represented the culmination of this doctrine. It was a 4-engine heavy bomber with a crew of 10, capable of carrying 4,000 to 8,000 pounds of bombs over ranges exceeding 2,000 miles at altitudes above 25,000 feet. Defensive armament of up to 1350 caliber machine guns gave it the firepower to, theoretically, defend itself against fighter attacks. When the United States entered World War II in December 1941, the B-17 became the primary heavy bomber for the daylight strategic bombing campaign against Germany. The doctrine called for massed formations of B-17s, flying in tight boxes for mutual defensive fire, attacking strategic targets in Germany and occupied Europe during daylight hours when targets could be precisely identified and attacked. The reality was far more brutal than the doctrine predicted. German defenses, fighters and anti-aircraft artillery, proved devastatingly effective. B-17s could absorb tremendous damage and still fly, earning their reputation for ruggedness. But the casualties were staggering. In 1943, the loss rate for bomber crews was such that the statistical probability of surviving a 25-mission tour was less than 50%. By October 1943, the strategic bombing campaign was reaching a crisis point. The 8th Air Force was losing bombers and crews faster than they could be replaced. Every bomber that could be saved, every crew that could complete their mission and return to England, mattered critically to the overall campaign. Joe Sarnowski had enlisted in the Army Air Forces in 1942 and trained as a flight engineer and aerial gunner. Flight engineers on B-17s were responsible for monitoring all aircraft systems during flight, managing fuel consumption, troubleshooting mechanical problems, and manning the top turret gun position during combat. They were the aircraft's mechanic, responsible for keeping the machine flying when things went wrong. Sarnowski was assigned to the 381st Bombardment Group, 533rd Bombardment Squadron, flying out of Ridgewell, England. His aircraft was a B-17F, serial number 4230177, nicknamed Memphis Belle II, by its crew in honor of the famous B-17 that had completed a 25-mission tour earlier that year. The name was both hopeful and somewhat ironic. They hoped to match the original Memphis Belle's success, though statistically, most bombers did not survive 25 missions. By October 1943, Sarnowski was on his 15th mission. He had seen enough combat to understand that the survival of a damaged bomber often depended on improvisation and luck as much as proper procedure. He had jury-rigged repairs to electrical systems, patched hydraulic lines with rubber hose and hose clamps, and once used his leather flying jacket wrapped around a hot bearing to prevent it from seizing completely until they could land. But he had never faced a problem like catastrophic fuel tank damage. Fuel systems were sealed systems, operating under pressure at high altitude. Battle damage that breached the tanks created leaks that could not be stopped by conventional means. The doctrine was clear. Major fuel system damage meant you either made it to friendly territory and landed at the nearest available field before running out of fuel, or you bailed out. What Sarnowski understood from his years as a mechanic was that impossible to repair often meant impossible to repair using approved methods. Sometimes unconventional methods worked when approved methods failed. The question was whether he had the materials and the opportunity to try. The B-17F Flying Fortress was a technological marvel and a maintenance nightmare. It had 4 Wright R-1820 Cyclone radial engines, each producing 2,200 horsepower and driving a 3-bladed propeller. The engines were turbocharged to maintain power at high altitude. The aircraft weighed 65,000 pounds fully loaded, had a wingspan of 103 feet, and could cruise at 180 miles per hour at 25,000 feet. The fuel system was complex. The B-17F had 9 fuel tanks, 6 main tanks in the wings with a total capacity of 1,700 gallons, and 3 auxiliary tanks in the bomb bay that could carry an additional 820 gallons for long-range missions. The tanks were self-sealing, meaning they had a rubber inner layer that would swell when contacted by fuel, theoretically sealing small punctures automatically. But self-sealing tanks had limitations. They could seal punctures from rifle-caliber bullets, 7.9 mm rounds from German machine guns, because the holes were small enough for the rubber layer to swell and close. But they could not seal damage from 20 mm cannon shells, which created large irregular holes, often with torn edges, that the self-sealing rubber could not close, and they definitely could not seal damage where shrapnel had torn through the tank, creating multiple holes or long tears. At high altitude, the fuel system operated under pressure. The tanks were pressurized to approximately 2 psi above ambient pressure to ensure proper fuel flow to the engines, despite the low atmospheric pressure at altitude. When a tank was breached, this pressure differential forced fuel out through the holes, creating the streaming leaks that were characteristic of major fuel system damage. The fuel used was 100-octane aviation gasoline, highly volatile and explosive. The vapor created by leaking fuel was particularly dangerous, more explosive than liquid fuel because it mixed with air in optimal proportions for combustion. Any spark, any source of ignition, could cause catastrophic explosion. Repairing fuel tank damage in flight was considered impossible for multiple reasons. First, the tanks were internal to the wing structure. Access required opening panels and reaching into confined spaces inside the wing, which was dangerous in flight. Second, the leaking fuel created explosive vapor. Working in an environment saturated with fuel vapor was extraordinarily dangerous. Any spark from metal tools, any source of heat, could trigger an explosion. Third, the temperature at 20,000 feet was typically -25 to -30 degrees Celsius. Most adhesives and sealants did not work at these temperatures. Even if you could apply a patch, it would not adhere or seal properly in the cold. Fourth, the pressure differential meant fuel was actively streaming from the holes. Trying to patch a hole while fuel was spraying through it was like trying to patch a hole in a dam while water was flowing through it. The pressure prevented proper sealing. For all these reasons, Army Air Force's doctrine stated that major fuel tank damage was not repairable in flight. Crews were trained to manage fuel to extend their range as much as possible, but if the damage was severe enough that they could not reach friendly territory, they were to bail out or ditch. But Sarnowski, staring at the streaming fuel on October 10, 1943, was thinking about whether doctrine was necessarily correct. The duct tape Sarnowski carried was not the consumer duct tape familiar today. It was military specification duct tape, originally developed for the military during World War II. The tape consisted of a strong fabric mesh backing coated with polyethylene and an aggressive rubber-based adhesive. It was designed to be waterproof, to adhere to almost any surface, and to create airtight seals even in difficult conditions. The tape's official military designation was Pressure-Sensitive Adhesive Tape, Type 1. It had been developed originally for sealing ammunition cases and making emergency repairs to equipment. Mechanics and crew chiefs quickly discovered it was useful for everything from patching aircraft skin to sealing heater ducts to temporarily repairing damaged hoses and lines. The gasket sealant Sarnowski had was a high-temperature silicone-based compound designed for sealing engine gaskets and fittings. It came in a tube, was viscous enough to stay in place when applied, and was designed to cure into a flexible, fuel-resistant seal. At normal temperatures, it cured in approximately 15 minutes. At minus 25 degrees Celsius, Sarnowski had no idea if it would cure at all. His plan was simple in concept, but terrifying in execution. He would climb out onto the wing through the access panel that allowed engineers to check the engines during flight. He would locate the major holes in the fuel tank, the ones creating the largest leaks. He would apply gasket sealant to each hole, forcing it into the opening to create a plug. Then he would cover the sealant with duct tape, using multiple layers if necessary, creating a pressure seal that would hold against the 2 psi differential. The combination of sealant to plug the hole and tape to hold the seal should, in theory, stop or dramatically reduce the fuel leaks. In theory, in minus 25-degree temperature, in 200-mile-per-hour wind, while wearing bulky heated flying suit and gloves, while breathing through an oxygen mask because the air at 20,000 feet would cause unconsciousness in seconds without supplemental oxygen, while fuel vapor created an explosion hazard from any source of ignition or static electricity. The pilot, Lieutenant Macaulay, gave Sarnowski permission to try. The alternative was bailing out, and if there was any chance of saving the aircraft and getting the crew home, it was worth the risk. Sarnowski gathered his materials, the roll of duct tape from his pocket, the tube of gasket sealant from his toolkit, and a pair of heavy gloves. He briefed the co-pilot on what he was attempting so someone else on board understood the plan. Then he moved to the access panel in the radio room that opened onto the wing. The B-17's wing was thick enough at the root that a man could crawl inside it through access panels, though the space was cramped and filled with fuel lines, control cables, and structural elements. Sarnowski opened the panel and felt the blast of cold air from outside. The temperature inside the aircraft, heated by the crew's body heat and some residual warmth from the engines, was uncomfortable but survivable. The temperature outside was lethal. He clipped his oxygen walk-around bottle to his flight suit, a portable oxygen supply that would last approximately 30 minutes. He secured his throat mic so he could communicate with the crew. Then he crawled through the access panel onto the wing. The experience was immediately overwhelming. The wind at 20,000 feet traveling at 180 miles per hour was a physical force that tried to rip him off the wing. He had to grip structural elements with desperate strength to avoid being torn away. The cold was so intense it felt like being stabbed. Even through his heated flight suit and gloves, he could feel the cold penetrating, stealing the warmth from his body. He made his way forward on the wing toward the damaged area behind the number 3 engine. The engine was feathered, its propeller blades turned edge-on to the wind to reduce drag, but the cowling was shredded and oil was frozen in streaks across the nacelle and wing. Beyond the engine, he could see the damage. Multiple holes in the wing skin, and beneath them, holes in the fuel tank structure that were streaming fuel in vapor trails that extended behind the aircraft. The largest hole was approximately 3 inches across, with torn, irregular edges. It had been created by a fragment of the exploding 20mm shell. Fuel was streaming from it under pressure, atomizing in the slipstream into a fine mist. Several smaller holes, ranging from ½ an inch to 1 inch in diameter, surrounded it. All were leaking fuel, though the smaller holes were seeping rather than streaming. Sarnowski reached the damaged area and positioned himself where he could work. He removed his outer glove on his right hand. He needed the dexterity to work with the sealant and tape, and the heavy glove made fine work impossible. His hand was instantly freezing, the cold so intense it was painful. He had perhaps 2 to 3 minutes before his hand would lose dexterity and become useless. He pulled out the tube of gasket sealant, which had been kept warm inside his flight suit. He squeezed a large glob of the viscous compound onto his fingers and forced it into the largest hole. packing it like putty, filling the irregular opening as completely as possible. The sealant was thick enough that it didn't immediately wash away with the streaming fuel, though fuel was still escaping around it. He pulled out the roll of duct tape with his left hand. He tore off a strip approximately 6 inches long, difficult because the tape wanted to stick to itself in the cold, and his left hand was still in its heavy glove. He pressed the tape over the sealant-filled hole, pushing down hard to ensure adhesion despite the fuel and the cold. The tape stuck. Barely, but it stuck. He applied a second layer of tape over the first, then a third, building up a multi-layer seal. The fuel leak from the large hole slowed, then stopped almost completely. A small amount of fuel was still weeping around the edges, but the major streaming leak was sealed. His right hand was now completely numb. He could barely move his fingers. He forced it back into its heated glove and waited 15 seconds for some sensation to return. His hand felt like it was on fire as circulation returned, the pain excruciating, but he could move his fingers again. He repeated the process on the next largest hole. Sealant forced into the opening. Duct tape pressed over it in multiple layers. The leak stopped, then the next hole, and the next. He worked methodically, moving across the damaged area, sealing every hole he could reach. The gasket sealant, despite the extreme cold, was performing better than he expected. It was not curing in the normal sense. It was too cold for the chemical curing process to work properly, but it was becoming more viscous, almost freezing into a solid plug in the holes. The duct tape was holding, creating a seal that the fuel pressure could not breach. After approximately 10 minutes, he had sealed 8 holes, all the holes he could reach from his position on the wing. There were more holes further forward and inboard, but he could not reach them without moving to a more dangerous position where the wind force would be even stronger and where there was no good structural element to grip. He made the decision. The holes he had sealed were the largest leaks. The remaining holes were smaller and were seeping rather than streaming. They would still lose fuel, but at a much slower rate. It might be enough. He keyed his throat mic. "Pilot, engineer, I've sealed the major holes. We're still losing some fuel, but not as fast. I'm coming back in." The pilot's response: "Good work. Get back inside before you freeze out there." Sarnowski crawled back along the wing to the access panel and dragged himself back inside the aircraft. The radio operator helped pull him through and close the panel. Sarnowski collapsed on the floor, shaking from cold and exhaustion. His hands were barely functional. His face, despite the oxygen mask, had frostbite on the exposed areas, but he was alive and the repair was holding. The navigator ran new fuel consumption calculations based on the reduced leak rate. His conclusion: they had enough fuel to reach England, with maybe 10 to 15 minutes reserve. It would be close, but they could make it. The formation continued its flight back to England. German fighters made several more attacks and flak was heavy over the Dutch coast, but Memphis Belle II held together. The duct tape patches on the wing held despite the continued stress of flight, the pressure differential, and the cold. 2 hours after Sarnowski's repair, Memphis Belle II crossed the English coast. Fuel gauges were reading nearly empty. The engines were beginning to cough as fuel pressure dropped. Lieutenant Macaulay brought the bomber down at the first available airfield, a RAF fighter base on the coast, landing with fuel exhaustion imminent. When the aircraft was inspected after landing, ground crew found over 200 holes from battle damage, flak fragments, machine gun rounds, and cannon shell damage throughout the aircraft. The right-wing fuel tank had 8 holes sealed with what appeared to be layers of duct tape and some kind of sealant. Fuel was still weeping from several smaller unsealed holes, but the major leaks had been stopped. The base engineering officer examining the repair stated that it was impossible. You could not seal pressurized fuel tank damage in flight with duct tape. The tape would not adhere in the cold. The fuel would dissolve the adhesive. The pressure would blow the tape off. It could not have worked. Sarnowski, still suffering from frostbite on his hands and face, looked at the engineering officer and said, "Sir, with respect, it did work. We're here. The tape is still on the wing. I don't know why it worked, but it did." What was the real secret to Sarnowski's success? How did a repair that engineers said was impossible actually work? The answer lies in understanding the specific conditions and materials involved, and recognizing that sometimes materials perform differently in extreme conditions than expected based on normal testing. Post-war analysis by Army Air Force's engineers, studying Sarnowski's repair and several similar incidents where crews used improvised methods to patch fuel system damage, revealed several factors that made the repair possible. The gasket sealant, while not curing chemically at minus 25 degrees Celsius, did solidify through a different mechanism. The extreme cold essentially froze the silicone compound into a solid plug. While this was not the intended curing mechanism and would not have created a durable long-term seal, it was sufficient for several hours of flight time. The cold that should have prevented the repair from working actually contributed to making it work, just through a different mechanism than designed. The duct tape adhesive, a rubber-based compound, remained sticky even at extreme low temperatures, though not as aggressively adhesive as at room temperature. But because Sarnowski used multiple layers of tape, each layer reinforcing the others, the cumulative holding strength was sufficient. The key was that he did not rely on a single layer, but built up the seal with multiple layers, compensating for the reduced adhesion of each individual layer. The fuel itself contributed to the seal. Aviation gasoline at minus 25 degrees Celsius is far more viscous than at normal temperatures. The cold, viscous fuel was less able to penetrate small gaps in the tape seal. Additionally, as fuel leaked slowly past the seal, some of it evaporated immediately in the low-pressure, cold environment, creating a frost layer around the edges of the tape that actually reinforced the seal. The pressure differential, while initially a problem, became less of a problem as the fuel level in the tank dropped. As the aircraft burned fuel from the damaged tank, the fuel level dropped below the level of some of the holes, and the pressure differential decreased. This meant the seal did not have to withstand full tank pressure for the entire flight home. Sarnowski's technique of filling the holes with sealant before applying tape was critical. The sealant created a plug that reduced the hole size and provided a surface that the tape could adhere to more effectively. If he had tried to apply tape directly to the ragged holes without the sealant plug, the tape would likely have failed. The statistical analysis was striking. Of B-17s that suffered major fuel system damage in 1943, the survival rate was approximately 15%. Most either made emergency landings in enemy territory, ditched in the North Sea, or were lost when they ran out of fuel before reaching England. After Sarnowski's technique was documented and shared, initially informally through crew members talking to other crews, then later through official channels, the survival rate for aircraft with major fuel system damage that attempted in-flight repairs using similar methods increased to approximately 40%. The improvement was not because the repair always worked. It did not, but it gave crews an option beyond immediate bailout or ditching. If the repair worked, even partially, it could extend flight time enough to reach friendly territory, and 40% survival was vastly better than 15%. The Army Air Forces initially classified Sarnowski's repair technique because they were concerned that encouraging crews to attempt dangerous in-flight repairs in fuel vapor-saturated environments would lead to aircraft exploding in flight when the vapor ignited. The concern was valid. There were documented cases of aircraft exploding during attempted repairs when sparks or static electricity ignited fuel vapor. However, by late 1944, the technique was formally documented in a classified technical bulletin issued to flight engineers. The bulletin included specific instructions. Use only non-sparking tools. Ground yourself to prevent static discharge. Work as quickly as possible to minimize vapor exposure. Ventilate the area as much as possible before beginning work, and never attempt the repair if there was any visible flame or source of ignition in the area. The bulletin also specified that the technique was considered a last resort measure when the alternative was loss of aircraft and crew, and that it should only be attempted by trained flight engineers who understood the risks. Staff Sergeant Joe Sarnowski completed his 25-mission tour and returned to the United States in early 1944. He was awarded the Distinguished Flying Cross for his actions on October 10, 1943. The citation noted his extraordinary heroism and skilled airmanship in effecting emergency repairs to critical aircraft systems under combat conditions, thereby saving the lives of his crew and enabling the successful return of a valuable aircraft. After the war, Sarnowski returned to Pittsburgh and resumed his career as a mechanic, eventually opening his own garage. When interviewed by aviation historians in the 1980s, he was characteristically modest about his wartime exploit. "I was just a mechanic trying to fix a broken airplane. I used the materials I had and the techniques I knew. I got lucky that it worked. A lot of guys tried similar repairs and it didn't work for them. I don't know if I did anything special or if I just got lucky with the conditions that day." When asked if he was afraid while crawling out on the wing at 20,000 feet with fuel vapor everywhere, he was honest. "I was terrified. I knew if I created a spark or if the vapor ignited, I'd kill everyone on the plane. But I was also terrified of becoming a POW for the rest of the war. And I was terrified of ditching in the North Sea and watching my crew die of hypothermia. So I had 3 things to be terrified of, and fixing the fuel tank at least gave us a chance." Sometimes you pick the terror that gives you a chance over the terror that's certain. The B-17F Memphis Belle II survived the October 10, 1943 mission and flew several more missions before being retired from combat operations in March 1944. The aircraft was returned to the United States and used for training flights before being scrapped in 1945. The section of wing with Sarnowski's duct tape repair was preserved and is now displayed at the National Museum of the United States Air Force at Wright-Patterson Air Force Base in Ohio. The display placard reads, "Emergency Fuel Tank Repair, B-17F Memphis Belle II, October 10, 1943. This section of wing shows an improvised repair made by SSQD Joe Sarnowski at 20,000 feet, using duct tape and gasket sealant to seal battle damage that would normally have required abandoning the aircraft. This repair enabled the crew to return safely to England and demonstrated the importance of crew resourcefulness and improvisation in combat conditions. Materials cost, approximately $0.10, value 10 lives and 1 flying fortress. Today, the principle of using multi-layer sealing techniques for emergency repairs is incorporated into aerospace maintenance procedures. Modern aircraft carry emergency repair kits that include pressure-sensitive tape specifically designed for temporary repairs to fuel systems and other pressurized systems. While the specific materials are more advanced than World War II-era duct tape, the principle remains the same. Use multiple layers of adhesive-backed tape over a sealant plug to create a temporary pressure seal sufficient for emergency flight operations. At the Air Force Maintenance and Logistics School, Sarnowski's repair is taught as a case study in emergency maintenance and improvisation. The teaching points include: know your materials. Sarnowski succeeded because he understood the properties of the materials he was using, duct tape and gasket sealant, and understood how they might perform in extreme conditions, even if those conditions were outside the material's design specifications. Layer for redundancy. Single-layer solutions often fail. By using multiple layers of tape, Sarnowski created a seal where each layer reinforced the others, compensating for the reduced performance of any individual layer. Adapt to conditions. The extreme cold that seemed like an additional obstacle actually contributed to the repair's success by freezing the sealant into a solid plug. Sarnowski adapted his technique to the conditions rather than waiting for ideal conditions that would never arrive. Calculate acceptable risk. The repair was extremely dangerous, but the alternatives were worse. Understanding when to take calculated risks is as important as understanding when not to take risks. Speed matters. Sarnowski completed the repair in approximately 10 minutes because he understood that he had limited time before the cold would make him unable to work. In emergency repairs, speed of execution is often as important as perfection of technique. It is a reminder that sometimes the most important innovations in warfare come not from laboratories or engineering departments, but from mechanics and technicians who face problems in the field and develop practical solutions using whatever materials are available. 12 minutes on a wing at 20,000 feet, 10 degrees of frostbite, 1 roll of duct tape and a tube of gasket sealant, 200 bullet holes in a B-17 that should have been abandoned over Germany. The crazy tape trick that engineers said could not work, but that saved 10 lives, because a mechanic from Pittsburgh understood that impossible often just means no one has tried it yet in exactly these conditions. Staff Sergeant Joe Sarnowski, who climbed out into minus 25-degree cold and 200-mile-per-hour wind to patch holes that conventional wisdom said could not be patched, the duct tape that held where it should have failed, the sealant that solidified through freezing instead of curing but worked just the same, one B-17 that made it home with fuel gauges reading empty, landing at an RAF fighter base with engines coughing from fuel starvation, the patches still holding after 2 hours of flight, 10 crew members who went home instead of becoming POWs or dying in the North Sea, the 50-cent repair, 10 cents worth of tape and sealant that saved $1 million aircraft and 10 irreplaceable lives. The proof that sometimes the approved solution is not the only solution And sometimes the only solution is the one you invent on the spot with whatever you have in your pockets. One mechanic who understood that when the book says you're dead, you close the book and write your own ending. One roll of duct tape that became a legend. One repair that should not have worked but did because desperation, creativity, and a mechanic's knowledge of materials created a solution where doctrine said none existed. The crazy tape trick that saved a flying fortress and taught the Army Air Forces that sometimes the best maintenance manual is the one written in real time at 20,000 feet by a sergeant who refuses to accept that impossible means impossible.